Hello everyone. So today we are going to discuss about design of bridges. So let us consider one problem. The problem is like this. Design the following bridge with total cross-sectional dimension of 9.2 meter. IRC class A loading is to be considered and distance of the cross girder is 3.5 meter assuming FE M20 M40 and FE 415 grade of steel. Okay, so this is the cross section that has been given to you. These are the longitudinal girders and we will be having the cross girder. If you see the top view, it will be something like this. We have these longitudinal girders and then we will be having some cross girders. Okay, these are the cross girders. These are the longitudinal girders. Okay, so this cross girders, the spacing is given to you at a distance of 3.5 meters. Okay, and we are asked to design this particular bridge with M40 grade of concrete and Fe 415 grade of steel. Okay, so if you can see here, so these are the main girders. This is the overall thickness of the slab, which is 200 mm, and these two part of the cantilever portion, there you can see this is the footpath, this is the railing. Okay, and here this upper portion is the wearing coat, which is a thickness of 80 mm. 80 mm wearing coat is there, and this footpath is at a height of 200 mm from the wearing coat. Okay, this height is mentioned here. The footpath is at a height of 200 mm from the wearing coat. Okay, so these are the railings, and here this distance, that means this distance is 120 mm. And the girders, the main girders, the thickness are 300 mm, and the spacings of the main girders are 3 meter. So this kind of bridges are called T girder bridge. So probably you have seen different kind of bridges. We have cable stayed bridge, then we have T girder or RCC bridge, then we have slab bridge. Like this we have different kind of bridges. Okay, so this particular bridge is called a T girder bridge because here you can see the girder is as a in the section you can see it's just a T. Okay, the flanges of this T are acting as a slab or the deck for the bridge. Okay, this is the flange of the beam. So this is that is why it is called T girder bridge. Okay, so let's go for the design. So we'll design this in small parts. Today we'll design only this cantilever portion. You just look into this. We'll only just design this cantilever portion. And as you have seen here, it is mentioned that we should design it for a kind of bridge, sorry, a double A kind of loading, which you can find it in IRC. So let's go for the design. So this is the cantilever portion, right? So if I have to show you the different dimensions, the footpath is of 1000 mm. Here you can see from this side to this side, this distance is 1000 mm or 1 meter, and up to this edge of the beam we have a distance of 600 mm. So total this distance of this cantilever portion is 1.6 meter. Okay, and the railing thickness is 100 mm over here. This is the wearing coat, this is the wearing coat over here, and this is 120 mm, and this end we have 230 mm. We have seen already in the previous drawing. Now you can see that if I want to find out the loading, so let's just divide. So suppose this is the railing part, we mark it as 1, then this particular rectangular part, is marked as 2, then this particular rectangular slab part is marked as 3, this triangular portion is marked as 4, and the wearing coat is marked as 5. Okay, so please remember this. If you have understood, we can go for the load calculation. First of all, let's find out what is the dead load. So the loads will be from the railing. The railing load is assumed to be 0.7 kilonewton per meter. Okay, so this load is going to act at the center of this 100 mm. So this is zero point 0.7 kilonewton per meter, and if I want to find out the moment, then this will be the lever arm, and this lever arm will be nothing but 1.6 meter, that because the total length is 1.6 meter minus 0.5 mm, sorry, yeah, 0.05. Okay, because this is 100 mm, you can see 100 mm divided by 2, up to this half of this railing will have the total load that is acting for the railing. So this lever arm is 1600 minus 100 by 2. That is what we have done here. And 1 mm, you just please ignore this 1 mm. I have just multiplied to keep the unit of the moment constant, which is kilonewton meter. So the moment for the weight that is coming from the rail is coming out to be 1.085 kilonewton meter. It is W into the lever arm. Okay. Now about the footpath, so you can see that is marked as 2. So let us show it again. So here this 2, this is the footpath. Now look at the figure. What is the height of this footpath? You can see here, already you can see the previous drawing that it is mentioned as 200 mm, and the wearing coat is 80 mm. So total height of this footpath is coming out to be 280 mm, and the total length of this width of this footpath is 1000 mm. It is given. So from this you can easily find out what is the weight of this footpath. So here you can see 0.28 into 1 meter is the width, 2.28 is the depth into 25, which is coming up to 7 kilonewton per meter. Now if you want to find out the moment, then the moment will act at the half of this footpath width, that means 1.6 meter, because 1.6 meter, because this weight will come about here, so it is 1.6 minus 1 by 2, that is 0.5, 1.6 minus 0.5 meter. This will be the lever arm. So that is what has been done over here. The moment due to the footing, this is the lever arm, you can see, and it is coming out to 7.7 kilonewton meter. Similarly, the slab reinforcement, sorry, slab rectangular, so the weight is the thickness is 1.2, so it is, sorry, 120 mm. The length is 1.6 meter, and the unit weight is 25, so it is 4.8. And if you want to find out the moment, it is 1 point, lever arm will be 1.6 by 2, half of this total distance, and it comes out to be 3.84. Similarly, for this triangular portion, you just find out the weight of this triangle. You can easily find out from the drawing, and which is coming out to be 2.2, and the moment is coming out to be 1.173 kilonewton meter. So, and another moment, that is another weight that is left with, is a wearing coat. The thickness of the wearing coat is 80 mm, and the distance or the length of this wearing coat is 0.6 meter only. So, and the unit weight of wearing coat is assumed to be 22, and from that we can find out the weight as well as the moment. The moment is 0.317 kilonewton meter. I hope this is not that tough. I think uh, you already know how to find the moment. Now if I want to find out the total dead load, you just add the weight due to rail, weight due to footing, weight due to rectangular slab, the triangular slab, and the wearing coat, which is coming out to 15.756 kilonewton meter. And if I want to find out the total moment, which is coming out to 14.115 kilonewton meter. Okay, so these are the total load due to dead load as well as the moment. Now we need to calculate the live load. So before going to the live load calculation, we know that the IRC class AA loading to be used, which is actually, if I take the track load, then these are some, suppose the tanks. Okay, the loading of the tanks basically we have to take. Now if I see how these loads are being arranged, so this is a type of class AA loading, and which has total width, the standard width is taken as 7.2 meter over here, and the the width of the track is taken as 3.6. Okay, so the important thing that to note over here is that what is the distance at where you are going to place your AA loading. Now this is a cross section of a bridge, and if the minimum distance from which the track loading should be provided is represented by C, and C is given as 1.2 meter. You can see from the edge of this footing, or the what to say, the footpath, the distance of the track load minimum should be 1.2 meter. But if you see our problem, if our footing, you can see for the cantilever, because as we are designing the cantilever now, just look at the cantilever and just forget everything else, just think about the cantilever. So in the cantilever portion we only have a distance of 600 mm available with us. So in that case we cannot provide a class AA loading to this particular cantilever, so because it is not possible. So the placing of class A loading for this cantilever is not possible, so we can go for next higher load, that is class A loading. Okay, so let's see what the class A loading looks like. So here you can see this is a class A loading type. um, Here are the different axle loads. The axle load over here is 114, and if I want to find out a wheel load, is divided 114 divided by 2. And sorry, these are basically, these are in kilonewtons, and these are, the lower one is for class B loading, this is for class B, and upper one is for class A. These are nothing but the axle loads. Okay, axle load, these are axle loads. So if I want to find out the wheel load, then it will be divided by 2, 114 divided by 2. Now where we can put it, so if you see the clear distance from the edge of the footpath, you can see it can be placed at a distance of 150 mm, and our available is 600 mm for the cantilever portion, because you can see that this is, suppose, the footing, and this is the cantilever what we have. Suppose this is the edge, this is the cantilever edge, so it is, we have 600 mm available with us, so we can easily put the loading of a class A loading. So that is why we are going to adopt class A, not the class AA loading. Understood? So this loading we are going to put, so for that please look into what is the loading. The maximum loading that we have is 114 axle loading, and if I want to find out the wheel load, it is 57 kilonewton, which is 114 divided by 2. Now let's place this particular loading over that our cantilever. Then we can see that, suppose this is the wheel, and we know that one wheel has a load of 157 kilonewton, which is 114 divided by 2. Then the placing is at a minimum distance of 150 mm. Okay, and we know that this we have available of 600 mm available with us. That means from here to here we have 600 mm. Okay, now let's look into the what is the dimension of the wheels that are available, that is given, or the standard dimensions. So you can see here the contact area, this is the contact area, suppose, so this is represented by B and this is by W. Okay, and the bridges will be somewhere here. Okay, the bridge will be something like this. This is the bridge, so the car is moving over here. So this is width, and this is B, the breadth and the width are given. So what are the values of B and D? If I am talking about the axle load of 114, the contact area is B is taken as 250 mm and W is taken as 500 mm. That means this width is 500 mm. So that is what we have to place for our drawing. Okay, so here you can see that this is nothing but 500 mm. Okay, so at the center it is 250 by 250. Now the thing is, when there is a loading of suppose any load that is acting, as we have a thickness of 200 mm. So now condition is how to take the load calculation, how to do the load calculation, as it has a thickness of 200 mm. In that case, what we do, we just distribute this loading like this. Okay, that means we assume that the load that is coming to the surface will get distributed in this triangular fashion. Okay, so this ratios, you can find out. So we can find out at what distance, up to which distance this particular loading expands, or this distance, this L, suppose we can calculate it out. Okay, so let's do that. Let's, and please understand this particular figure, because we will be using this figure. Now here you can see that considering only cantilever portion of the class AA loading is not possible, as only 600 mm of clear distance is available, right? So instead of class A loading can be used as class A loading. 150 mm of offset is sufficient. Okay, the distance of the center of gravity for the class A loading for our case, that is the center of distance, we can calculate. So at which distance where this particular loading is acting, which is 600 mm minus 150 minus 250, that means 200. After at a distance of 200 mm the center of this particular loading is acting. So if I have to show you the figure, I think you will understand. That means we want to find out, we are interested in what is this distance. This distance, that means the point of action of the load and the edge of the beam, at which distance the load is acting. So this is, you can find out, because this total distance is 600 mm, then we know this 150, and this is, we know this is 250. So you subtract 150 and 250 from 600 mm and you will end up with 200 mm. So that is the lever arm, you can say, or the position of the load from the edge of the beam. Now let's find out the dispersion length. The dispersion length can be calculated by like this. Suppose we have this thickness and we have a loading over here, and this is suppose L and thickness is T. Okay, then the total dispersion length, this is suppose X, then X can be given by L plus 2D. Sorry, okay, L plus 2D, because this is also D and this will be also D. So L plus 2D will be the X. Okay, so that's equation to be used. Then the total width of our loading is 500 mm. Then total thickness we have, the overall thickness of the slab is 200 mm, then wearing coat of 80 mm is there. The total thickness is 280 mm into 2, then you will end up with around a value of 1060 mm. This is the total width. Now look at this figure. Sorry. Now look at this figure. From our calculation we got that this distance from here, it is 1060 meter to this distance. Okay, this is the overall distance, which is 1060 meter. Now you can see that only available length is 600. We have up to this distance, but for the cantilever portion, is this portion of loading is important. This portion of loading is not important for us, because that is in the other side of the edge of the beam. So on, for our case, only this portion is important, right? So what is this, or what is the, what to say, the length of this portion, that you need to find out, because we only need this particular portion. Which portion? If I say this black portion, this portion is important for us, because that will give rise to the moment and the shear force that will be required, the moments and shear force that will be required for our design. So what is this length? So let's calculate that. So that distance will be the dispersion length plus that the distance of the center from the edge of the beam. So here you can see, suppose this is the center, so this is the half of this 1060 mm, so it is coming out to be, so this is 1060 by 2, this is 530 mm, right? And this distance is 200 mm, so total is 730 mm. So this distance from here to here, this is nothing but 730 mm. Clear? So this is 730 mm. So the actual contributing wheel load, so if I want to find out what is the actual contributing wheel load, then we can 57 kilonewton is being dispersed over the actual dispersed length, but we are only considering only 730. So actual wheel load for this, for the length of 730 mm, will be 39.255 kilonewton. So this particular load is important for us because this load only give rise to the moment and shear force that will be required for design of the cantilever portion of the bridge. Then effective width. Now just we are only looking at the cross section. Now if I look from the top, suppose this is the railing portion, this is the footpath portion, and then we have this edge of the beam. Okay, so total we have 1600, this is 600. Okay, so the loading is being placed over here like this. So this distance we have already calculated, the dispersion length is 730. This dispersion length we have calculated, but in the other side also the width is also is required, because up to what is the width of this particular load, because the load is not being only dispersed in only one direction, it will be dispersed into all the directions. Okay, so it is a two-dimensional distribution, it's not one dimensional. So if we have, this is 730 we have calculated, but also we have to find this be dispersed, this portion we need to find out. So how to find out? This can be found out by this equation, 1.2 x plus b1. What is x here? X is nothing but that 720, and b1 we need to calculate. Okay, now x is not this one, x is not this one, x is nothing but half of this actual, half of the actual dispersed length. Okay, the actual dispersed length was uh, yeah, actual dispersed length was 730, so 730 by 2, that is 365. So this is something you need to remember, this is the equation. So 1.2 of x is nothing but the actual is how much? X is 730, so 730 by 2, that should be considered as x. Okay, to find out the b, so it is 1.2x plus b1. B1 is what? B1 is how you are going to disperse. Okay, so okay, so the b1 is nothing but it can be calculated as the width of the wheel. If you remember, the wheel, the contact area, the width is all given by 250, and this was given by 500, remember, for the wheel load distribution. So this width 250 will be used here. Okay, and then this is 0.08, this is the wearing coat thickness, this is the wearing coat thickness. Okay, so the b1 is nothing but the width plus the wearing coat plus 2 times of wearing coat thickness, that will give you b1. So if you do this calculation, then you can find out what is the b dispersed. So b dispersed is coming out to be around 848 mm. Okay, I hope this part is clear. So what is x? X is nothing but whatever actual dispersion length we have calculated, which is 730 divided by 2, that will be x, and b1 is nothing but the width of the wheel that we take from that standard IRC, and then plus 2 times of the wearing coat, whatever thickness of the wearing coat we have. Okay, So if you add these two, we'll get B dispersed. Then one other thing that you need to consider is the impact factor. So what is impact factor? Basically that whenever we consider the loading, that is suppose the wheel loading that is moving, right? So there will be some sudden braking or certain acceleration. So this kind of behavior you can see in case of bridges. So this will impart some additional load to that. So that is why we need to consider some impact factor. So impact factor, you can calculate it out by this formula. Here 4.5 and 6 are some constant and 1.6 is the length of the cantilever. Okay, so these are some constant. So these two value it is can be represented as A by B plus L. A and B are constant which has a value of 4.5. Okay, so the A value and B value we can find out from here, and the L is nothing but the length of the cantilever. Then maximum impact factor, okay, the impact factor that we have calculated is around 0.592, and actually the maximum impact factor taken is actually zero point 0.5. So we'll take for zero point 0.5. Then bending moment due to live load. Now let's calculate the bending moment. The bending moment will be the with the load W will by the B of dispersed. Okay, the width of the dispersed, that will be the loading. Okay, so what is will load? You can see over here. If I show you, the will load is 39.255, right? So this is what the total load was, which was in kilonewton, but that load is being distributed up to over a effective width of B dispersed, right? So per unit meter or per unit meter, if you want to find out, then that will be the will load divided by the dispersed width. Okay, that will give you the load kilonewton per meter. Then that will be multiplied with the effective length or the lever arm. So what with the lever arm over here? The lever arm will be whatever actual dispersed length we have, L dispersed actual divided by 2, and this 1.5 is because of the impact factor. Okay, 1.5, and 1 meter is to just keep our moment unit constant, which is the final calculation. After final calculation, the value we get is 25.344 meter. Okay, so that is the live load moment. So if I want to find out the design moment, then you can find out 1.5 times of dead load plus live load moment, which comes out to be 59.189 kilonewton meter. And the shear force, if you want to find out, then it will be total load. So dead load W, this is a dead load into 1.5, and I have multiplied because of this impact factor. Okay, this 1.5 into 1.5 because this is the factor, design load factor, dead load 1.5, dead load plus live load, that is 1.5. This is 1.5 is the partial safety factors, and this 1.5 is actually the impact factor. Okay, and the shear force is coming out to be 1.957 kilo Newton. I think you have understood so far. So now as we have the moments and the shear forces, we can go for the designing. So let's find out first the effective depth. So assuming the average depth of the slab is 200 mm, then 8 mm bar we can assume, then and 25 mm of clear cover, not 8 mm bar, basically 16 mm bar we are assuming. So half of the 16 mm bar, that is 8 mm, and 25 mm clear cover, then effective depth comes out to be 167 mm. Now if I want to check for the effective depth, this part is basically as simple as designing of a cantilever beam. So if I want to find out MU limit and find that, from that you can find out the D required, which is 103.55 mm, and we have the effective depth available as 167 mm. So obviously this is okay. Now we will go for the calculating the moment, sorry, the steel, and the steel comes out to be around 1050 mm square. And if I want to find how many numbers of bars or the spacing of the bars required, then 16 bar if I place, then it comes out to be around 191.346. And as this is a little bit high, we can provide 16 bar at a spacing of 150 center to center. Okay, now this is actually the main reinforcement, right? And now what about the distribution reinforcement? The distribution reinforcement is provided by calculating in distributing moment. The distributing moment is calculated by this equation, which is 1 point sorry 0.3 times of the live load and 0.2 times of the dead load, which is again being multiplied with the partial safety factor, which comes out to 15.639. And the effective depth and available considering 8 distribution bar. Okay, so initially whatever whatever reinforcement we have given 16 bar, those are provided. Suppose this is the cantilever, so bars are provided at the below. Okay, then the distribution bars will be provided over that main bars. Okay, so for this distribution reinforcement, the effective depth will be reduced now. So what, how much will be reducing? So if overall depth d, then minus, okay, I think here we should have 6, sorry 8, yeah, 8 another 8 I will subtract from the whatever d we have already calculated, and 4 is for d, is 8 bar. Okay, 8 bar, d by 2, that is 8 by 2. Okay, that will be 4. And this 8 basically, because we have 16 bar, we have provided initially the effective depth we have calculated the center of the main reinforcement bar, that is 16 bar. Now we have to provide the effective, we have to calculate the effective depth up to the center of this 8 bars, which is at the above the main bars. So another 8 I will subtract and another 4 I will subtract, and I will get effective depth of 0.155 meters. And for that we can calculate the area of steel, which comes to 284.914 square. And if we find out the area of steel, sorry, number the spacing, then we can get 176. So let us provide 8 bar with a spacing of 150 center to center as distribution reinforcement. Okay, so now we have already calculated the moments and the moments reinforcement required for moment as well as the distribution reinforcement. So now you can check for the shear reinforcement. Okay, and as you can see that for the reinforcement that we have provided, as we cannot provide the shear reinforcement in the slab, so we have to provide adequate numbers of reinforcement so that, or percentage of steel, longitudinal steel, so that it can take that shear that is coming to it. Okay, so I'm leaving the shear design part to you, and up to this part I think you have understood, and with this we can conclude that this is how we can design a the cantilever footing portion of a bridge. The design part, basically the most important part is the load calculation part. If you understand that part properly, then other part is just a simple cantilever beam design. Okay, so with this I would like to conclude today's class. Thank you.